So as we've been talking about different ways that we can apply our planar kinetics of a rigid body, first with our forces and accelerations, and then the last couple of videos we've been talking about work and energy. And so we said, all right, one way we can apply that is through our principle of work and energy, where we say T1 plus all of the work done by all of the forces that do work, that cause displacement, equals our final kinetic energy, right? And so that was the same equation that we had used for our particle kinetics, right? Back towards the beginning of class, back in the first half of class, we used that principle of work and energy, and it's still applied for our rigid bodies. And so just as that was true, it's also true that we can apply our conservation of energy for rigid bodies as well. So when we have these rigid bodies that are undergoing planar kinetics, right? So that's your translation, that's your rotation about a fixed axis, that's your general plane motion. When a rigid body is going through those motions, we can use our conservation of energy. So that conservation of energy is T1 plus V1, and that's our initial kinetic energy plus our final kinetic energy, initial kinetic energy plus initial potential energy, right? So initial kinetic, initial potential equals the final kinetic energy, T2, plus the final potential energy, V2. And this is just the same equation that we saw, back in the first half of class. Our conservation of energy equation still applies, still works just the same way. And actually, our potential energies aren't even any different for a rigid body. We still only have two things that can cause our potential energies, which is either the gravitational potential energy, and that comes from your weight times delta y, or you could have potential energy from a spring. So this is from weight, this is from a spring, which is 1/2 ks squared. We have the gravitational potential energy or elastic potential energy. Those are the only places our potential energy can come from. And then our general form for our kinetic energy, now that we have rotation to deal with, it's going to be our 1/2 mv squared plus 1/2 ig omega squared. And depending on the context, you can still use some different variants of this kinetic energy equation. If you have rotation about a fixed axis, you can use 1/2 io omega squared. Or if you have rolling without slipping, you can use 1/2 IC or IIC omega squared, and that's your moment of inertia about the instantaneous center of zero velocity. Since there's no velocity there, it eliminates that velocity term, so you just have 1/2 IIC times omega squared. And then it's just applications of these just as we have seen before. Right? So the key with our conservation of energy is knowing when you can use it, right? So you can only use it if there are no forces, no non-conservative forces that do work, right? So those non-conservative forces are things like friction or applied loads. Those are our non-conservative forces. There are others, you could have thermal or other forces, but if there are only conservative forces acting on a system, so that's your weight and your springs, or forces that don't do any work whatsoever, like a normal force, then you can use conservation of energy, and it can save us a few steps here. So we're going to take a look at a couple of examples today of how to apply this conservation of energy specifically for rigid body scenarios. Alright, so for our first example here, the wheel shown has a weight of 30 pounds and a radius of gyration of k equals 0.6 feet about its center of mass g. It's attached to a spring which has a stiffness of k equals 2 pounds per foot and an unstretched length of 1 foot. The wheel is released from rest in the position shown and rolls without slipping. Determine its angular velocity at the instant g moves 3 feet to the left. So g is moving 3 feet to the left. It's going to come from where it is now. Right, so this g is right here. It makes this little 3, 4, 5 triangle. We can see this 3 foot, 4 foot. That tells us this length of this spring here is going to be 5 feet. And this G is moving to the left by 3 feet. So this is going to come over here. The new position of this disc is going to be vertically right under this pin where this spring is stretching out from. Okay, so that's kind of the movement. This disc is going to kind of roll along the ground over to where it is positioned directly under that pin that the spring's attached to. So first things first, we're just going to draw our free body diagram and a kinematic diagram that could help with that. So for our free body diagram, again, I'm just going to focus on the wheel here. Right? The spring isn't necessarily part of the system, it's just a force. It's contributing a force to the system. So we have this wheel. It has a weight of 30 pounds, so we know that acts at the center of the wheel, G. A weight of 30 pounds. We know that that spring is contributing a force that's pulling on G. Right? That spring contracting is what's causing the motion. Right? That's what's causing it to move to the left by that 3 feet. We have the force from the spring, and then the only other force that we have here is the normal force from this wheel interacting with the ground. And then they do tell us that it rolls without slipping. So that's just something we'll note in our head, that this rolls without slipping. That's really going to come into play over here in our kinematic diagram. So in our kinematic diagram, I draw my wheel. Again, I'm just labeling my velocities, angular velocities, any displacements that may be helpful. So my kinematic diagram, I'm going to have an angular velocity this time that's going counterclockwise as we're rolling to the left. And because we're rolling without slipping, I know that my center of my disk here is moving with velocity v sub g. I also note that for rolling without slipping, I have an instantaneous center of zero velocity, an IC point at the very bottom where this wheel is interacting with the floor. And so the reason that I bring up that IC point there is because I have two ways of approaching my kinetic energy. Right? I can either approach it by using 1/2 mvg squared plus 1/2 ig omega squared, or I can use a kinetic energy formula with just the IC, making the velocity component 0. IIC times omega squared times 1/2. So I have two options I can use for kinetic energy here. But I'm getting a little bit ahead of myself because first I want to just make sure that we can use conservation of energy here, right? So when we're analyzing these problems, then we need to decide, okay, now that I have that free body diagram and kinetic diagram, what's the method I want to use? Do I want to use equations of motion? Do I want to use work and energy principle? Do I want to use conservation of energy? Do I want to use impulse and momentum? And if I look at what I have going on here, the only force that's doing any work at all is spring force, right? The spring is the only thing that's doing work. Our weight isn't doing any work because there's no motion in the y direction. That normal force isn't doing any work. There's no force, or there's no displacement in the y direction. So the spring force is the only thing that does work, and since that's a conservative force, we can use conservation of energy, right? No applied forces, no frictions, no non-conservative forces are at play. So this is a great contender to use conservation of energy, especially because we're trying to find an angular velocity. Right, so anytime you're looking for velocities or angular velocities, conservation of energy or principle of work and energy is a really good call. Alright, so we've decided we drew our free body diagram, we drew our kinematic diagram, kind of decided what was going on, and then we said, okay, let's apply our conservation of energy. So initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy. So looking at our free body diagrams and kind of everything that we have here. For T1, that's our initial kinetic energy. Let's look at our prompt here. Does it tell us, do we have an initial velocity or an initial angular velocity? The wheel is released from rest. Wheel is released from rest. So that tells us no initial kinetic energy. That's easy enough. That one's 0. Then we're going to look at our initial potential energies. Right, so we said the only thing that has a potential energy here, the only thing that is doing any work that can have any potential is that spring force. So the potential energy for a spring is 1/2 KS1 squared. Right, so S1, that's your initial position, right? Your initial stretched value of your stretched value minus your unstretched value. Right, how much, what is the displacement of the spring? How much is that spring displaced? Then we're going to come over to the other side of the equation and we say, okay, my kinetic energy final, what do I want to use for that? And so that's where we're going to come back here to these guys and say, all right, I've got two choices. I can either use 1/2 mv squared plus 1/2 ig omega squared, or I can use 1/2 IC times omega squared, which the one I'm going to show you in this example, because it's probably the one that you're a little less comfortable with. So I want you to like just see it and get a little bit more comfortable with it, but just know you could do either way. You could solve this either way with whichever kinetic energy formula you wanted. But since this is a rolling without slipping problem, I'm going to say, okay, great. I'm going to use 1/2 times moment of inertia about IC times omega squared. That's what I'm trying to find, right? I'm trying to find that omega. And so that's entirely my kinetic energy. And then finally, I'm going to have that potential energy. And my potential energy, again, only coming from the spring, 1/2 KS2 squared. Right? Whatever that second distance for the spring is, that second displacement for the spring. Let's start plugging numbers in here and see how far we can get. 0 plus 1/2 times k, the k value, they gave us, again, not the radius of gyration here, but the stiffness constant. That stiffness coefficient, k equals 2 pounds per foot. 2 times s. So originally it has an unstretched length of 1 foot. And in its initial position here, if we look at the diagram they gave us, we know that that length is 5 feet. Right? We said that this was a 3, 4, 5 triangle. And so that initial length of that spring is 5 feet. So we need to take that 5 feet minus its unstretched length to give us how much it's been displaced. That s value is 5 minus 1. And then we're going to square it. And we're going to move on to our other side, do our kinetic energy here. So 1/2 times moment of inertia of IC. So our moment of inertia, we have a few different formulas for it. We can either look it up, or in this case, did they give us a K? They sure did. They gave us that radius of gyration. So with that K value about G, AG is 0.6. So that tells us IG is M times K squared. So my IG, the mass on this guy, 30 pounds is his weight. So his mass is going to be 30 over 32.2 times the K value of 0.6. Square that. And that gives me IG. And again, if I wanted to just keep this IG value of 0.335 that we found, I could use it. I could use it in this top T value right here. But since I said I was going to use this IIC, I'm going to convert this over into my moment of inertia of IC, which is just IG plus mass times the distance between G and IC squared. Mass times the distance between G and IC squared. 0.335 plus mass is 30 over 32.2 times the distance between G and IC, which in this case is just the radius. Here's G, here's IC. That radius is 0.75, so 0.75 squared gives me a moment of inertia about IC of 0.86. And the units on this again are slug times feet squared. Slug times feet squared. I'm going to pop this guy in here for IC. 0.86 times omega, that's what I'm looking for. I'll keep it in there as omega squared. And then finally, we're going to have the final potential energy of that spring up here. When that spring is in this position, scroll up a little bit more. So when our spring is in the final position, this disk is right here, right? Our spring is vertical, so the spring is now only stretched out by 4 feet instead of 5 feet. So that means we're going to have 1/2 times the k value of 2 times 4 minus 1 squared. Right? Remember to subtract out that that unstretched length. And it's all numbers, right? From here, it's just a matter of plugging this into your calculator to solve for our angular velocity. And when we do that, we're going to get an angular velocity of 4.04 radians per second. And so after that disk travels 3 feet, our angular velocity is 4.04 radians per second. Let's take a look at one more example. All right, so for our last problem today, we have a pavement compactor that's traveling down an incline at a velocity Vg equals 5 feet per second when the motor's disengaged. Determine the angular velocity of roller B, so that's our front wheel there, the one that's more to the right, roller B when the compactor has traveled 20 feet down the plane. Body of the compactor, excluding the rollers, has a weight of 8,000 pounds and a center of gravity at G. Each of the 2 rear rollers weighs 400 pounds and has a radius of gyration of Ka equals 3.3 feet. And then the front roller has a weight of 800 pounds and a radius of gyration of Kb equals 1.8 feet. Rollers do not slip as they rotate. All right, so we have got another problem where we have rolling without slipping, this time for 2 wheels that are moving together along the ground as this tractor moves down the incline, right? So the only way this thing is moving down the incline is by gravity, right? It had an initial velocity, the power was cut, and then the only thing that's keeping it going is the weight of the vehicle itself causing the movement down the incline. So let's go ahead and break out our free body diagram of this guy. Right? I know there's a lot of information here and it can feel really intimidating with this image and you maybe aren't so sure where to start, but a free body diagram is going to be your best friend. It's going to really help you analyze what's going on, pick out what's important, and figure out what you're figuring out, really, more than anything. So for our free body diagram, and again, he's free body. He can be pretty, I'm not going to be very, well, that's a tractor. Again, he's not perfect. He's a free body. And he is traveling on this incline. Maybe I'll draw that a little better. There we go. He's traveling down this incline of 30 degrees. All right, so I'm going to look at my free body diagram for him. They told us that, put this on the side, the initial velocity of Vg is 5 feet per second, then the motor's disengaged. We want to find the angular velocity of B when the compactor has traveled 20 feet. So omega B equals question mark, and the compactor has traveled 20 feet. So I'm going to just say distance, for now we'll just call it distance, is 20 feet down the plane. Right, that's our displacement. You could say S is 20 feet, whichever you prefer. I guess S makes a little more sense. Let's change that. And then again, just picking out stuff from my prompt up here so I can write it down and also stick it on my free body diagram. The body of the compactor, excluding 2 rollers, has a weight of 8,000 pounds at G. So we can see G over in our diagram acts right about here, and that has a weight of 8,000 pounds. And it tells us we have 2 rear rollers, which we can't see from this side view that they gave us, but there are 2 rear rollers at A that weigh 400 pounds each. So 2 rear rollers, 400 pounds each, means that we have a total of 800 pounds acting at A, right? 2 times 400 is going to be 800 pounds. And then the front roller also has a weight of 800 pounds. So at B, we also have a weight of 800 pounds. And then the rollers do not slip as they rotate, so there's no friction there. And we know that because these wheels are on the ground, there is a normal force at A, and a normal force at B. So now that we have that set up, we say, okay, I have an initial velocity. I want to know a final angular velocity. I only have weight forces that are doing any work. So those are all conservative forces, which means there are no non-conservative forces, and we can use conservation of energy, right? So we're going to go ahead and use our conservation of energy equation. T1 plus V1 equals T2 plus V2. So let's break down each one of these guys. T1, our initial kinetic energy, is going to be for this system as a whole. So we have to think about every single thing here that contributes to that initial kinetic energy. And we have energies from 3 different aspects, right? Not only do I have my kinetic energy from VG1, right? So this is G here. There is a velocity down the hill, VG1. But I also have angular accelerations around my A and my B. Omega A and omega B. Those all contribute. Each one of those exist, and they have to go into that initial kinetic energy calculation. So for T1, I need to account for 1/2 mvg1 squared. And they gave me VG1, so that'll be a simple substitution. Plus 1/2 IGA times omega A initial squared. Plus 1/2 IGB omega B initial squared. All of those components have to go in here. Because we have those 3 different masses, those 3 different movements, where you have the velocity that's causing a movement for the tractor mass, and then those angular velocities that go with each of those rollers, all of those get their own component there in the kinetic energy equation. So before we move on, I guess it would be good if we went ahead and found what IGA and IGB are. And they did give us the radius of gyration for A and for B. So for A, IGA is going to be the mass of A times Ka squared. So mass of A we decided was 800 pounds, or 2 times 400 pounds. So 2 times 400, and since those are in pounds, they have to be converted back out to slugs. So divide that by 32.2 times the K value of 3.3 squared. So IGA is going to be, I guess I didn't calculate this out, I just left it in my, let me pull a number for this real quick. Did I not? I can't believe. You know, sometimes I'm good in my notes and I leave myself numbers, and other times I just jump ahead before I calculate anything. Alright, so we have 800 over 32.2 times 3.3 squared. Alright, so that gives me, that seems kind of high. 800, 3.3 times 3.3 divided 32.2. Alright, 270.6, the number that I'm getting. Slugs, that's slugs times feet squared. And I can do the same for IGB equals MB KB squared. And my KB is 1.8. So that's 800 over 32.2 times 1.8 squared gives me IGB of another number I didn't write down, 800 divided by 32.2 times 1.8 squared, 80.5 slug feet squared. Okay, so with all of those, I can go ahead and plug in numbers here. So T1, I'm going to have 1/2 times the mass of the tractor, which was 8,000 pounds, over 32.2, times VG was given over here, 5 squared, plus 1/2 times my IGA, which we said was 270.6, times omega A squared. Ooh, do I know what omega A is? Right, since these rollers are rolling without slipping, I know that it has to hold true that my VG equals omega times R. So since my A and my B are different radii, my omega for each of them is just going to be VG over the radius of each one. So for omega A, that's going to be my VG was 5, there we go, 5 feet per second, divided by the radius of A. I look back up here, my radius of A, 3.8 feet. So that's over 3.8, and we're going to square that. Plus 1/2 IGB is 80.5 times omega B, which we said is VG over R, so 5 over its radius, and its radius is 2.2 feet. And we're going to square that. So that's just a number, right? Like that just spits out for us T1 equals 4168.8 pound-feet for our initial kinetic energy. Just a number from the calculator. Now we're going to go ahead and look at our initial potential energy. Right, so our initial potential energy, V1, here we only have potential energy from weights. So I'm going to say that at the top of the hill is where we have potential energy, and then when it goes down that 20 feet, when it reaches the bottom of the hill, I'm going to say that's where we have 0 potential energy. So when we're up here, I'm going to say that whatever height this is at, this is the starting height, that's going to be our initial potential energy. So our V1 is going to be weight times the height, right? Sometimes you see it as like mgh, but in this case, we're already given weights. So I'm just going to do weight times the height that it's moving down, right? It's moving down those 20 feet. So in this case, the weight is going to be the total weight of the whole compactor contraption. So that's our 8,000 plus the 2 times 400 for the rollers at A, plus the 800 for the roller at B. And then I need the distance that is traveling, right? I need that H value. Because we know that this tractor is going to roll down the hill by 20 feet. It's moving 20 feet this way on this 30 degree inclined slope. So what I'm looking for is I'm looking for the height, right? What is this height that it's going down? And if I look at this guy, I can see pretty clearly I can get that height value by doing 20 sine 30. So I can multiply this guy by 20 sine 30 to get that height. And again, that's just another number. No unknowns are in here. It gives me a potential energy of 96,000 pound-feet. All right, so that's just the first half of the equation. We still have to do this second half. Thankfully, we already decided, we said, all right, my V2, the bottom of my hill here, right, my tractor starts here, goes to the bottom. I said V2 is going to be 0. That's going to be the datum for this. No potential energy at the bottom of the hill from our weight. But we will have a kinetic energy because that's what we're trying to find, right? We're trying to find what the angular acceleration is, not acceleration, sorry, angular velocity. Well, if I just read the words on the screen, that would be better. What the angular velocity is for roller B after it's traveled that 20 feet. So again, we're going to use this same T setup, right? This same kinetic energy setup that we had right here. We're going to use this exact same equation, just now all for final values instead of the initial values. So T2 is going to be 1/2 mvg2 squared plus 1/2 IGA times omega A final squared plus 1/2 IGB times omega B final squared. Now remember, these still hold true, right? It's still true that VG equals omega times R. So what I'm going to do to strategize for this final thing here, I know I need to find an angular velocity, but the problem is that I really have 3 unknowns here. Right? I'm going to have a VG, I'm going to have an omega A, and I'm going to have an omega B. So I want to get that to just one single unknown so that I can actually make this solvable, and then I can work back with these relationships here. So I'm going to start plugging some things in here. So for my T2, 1/2 times the mass of the whole thing, that 8,000 over 32.2. And then I don't know what that VG is, so I'm going to leave it as VG squared. I might just leave it as VG squared. VG squared. Plus 1/2, and then my moment of inertia about GA doesn't change. So that's still going to be that 270.6. And then is this omega A that's a little bit different. Right, this omega A. Instead of writing omega A, I'm going to substitute in VG over RA. And what was that radius of A? It was 3.8 feet. So I'm going to substitute in here VG over 3.8 squared. Right, because now if I use that substitution instead of keeping it as an omega, I'm only going to be left with velocities, right? Just with that VG term. So plus 1/2, and then moment of inertia, GB, that doesn't change, 80.5, times omega B final. So instead, I'm going to substitute in B over the radius of B. Radius of B is 2.2. 2.2 squared. So my final step in this is that I can take all of these values and actually set up my conservation of energy equation that we had right here. So in this case, T1 plus V1, so that's 4168.8 plus V1, 96,000 equals T2, just T2, which is this entire, you know what, I'm going to put this as this whole thing equals T1 plus V1, which were those values of 4168.8 plus 96,000. Here we go. So now we can see this is all together in one big equation where I can substitute things into my calculator and solve for this velocity. I can solve for what that VG is. And when I find that VG is 24.5 feet per second. And then I can substitute that in over here for omega B equals VG over RB. So omega B equals 24.5 over RB of 2.2 gives me an omega B of 11.1 radians per second. And so we were trying to find that angular velocity just of the roller B. So it's a lot of setup, but it helps make your math a little bit simpler. So it seems really cumbersome and seems really long, but this is actually a much shorter way to do it than trying to brute force your way through the kinematics, through your equations of motion in more longhand forms. These equations do shortcut you even when they don't feel like it, right? You can use these, your working energy, your conservation of energy, if you have the right scenario where you have no non-conservative forces. Just know that the setup takes a little bit of time and understanding of the problem, as it does with a lot of our problems in dynamics, right? So conservation of energy, really great to use when you have no non-conservative forces, like weight and springs. And it'll help get you to an answer a little bit faster, even if it doesn't necessarily feel like it.